So, good morning to Dr. Hariza and Dr. Siti. So,
My name is Muhammad Shahriza bin Abdul Hai. My metric number is 201061320. Today, me and our team will present about our mini project assignment, semester 2 2021-2022, subject EMJ 37504 Control System Engineering 2. This slide and video created by our team. Our group members, firstly, our group leader is Lavenia, anak perempuan Gopal. Second, Ben Junho. Third, Nur Zahira binti Abdul Khalid. Fourth, Muhammad Muklis bin Kamaruddin. And fifth, that's me, Muhammad Shahrizan bin Abdul Hai. Then our subject is lecture by Dr. Hasrizal bin Hassan Basri, Dr. Siti Mhanis binti Otman. Then I will pass to Zahira for introduction for our mini project.
My name is Nur Zahira binti Abdul Kadi, 201062253. For the introduction for our mini project, an inverted pendulum is a pendulum with the center of mass above the pivot. It is frequently used as a card and a pole since the pivot point is put on a card that can move horizontally. Most applications limit the pendulum to 1 degree of freedom by affixing the pole to an axis of rotation. An inverted pendulum must be actively balanced to remain upright because it is inherently unstable when hanging downward. Modeling inverted pendulum system in state space representation is like this. The output performance of the system will be unstable. In that case, the pole placement will destabilize the system. What is pole placement? Pole placement is to stabilize an unstable system by manipulating the pole locations of a system and to improve the transitions in response to the desired design of the system. At the same time, the output will be produced an enormous error. Therefore, to improve the steady state system, error must be used a PID controller. PID stands for Proportional Integral Derivative. It's a control mechanism employing feedback that is widely used in industrial control system. PID controller continuously calculate an error to check the difference between the desired output set point and measure process variable and applies a correction based on proportional, integral, and derivative terms. The controller has feedback loop, which is the most accurate and stable controller. PID automatically corrects a control function in a precise and timely manner. The objective of our mini project, firstly, to design a controller to enhance the card inverted pendulum system with a pole placement controller. Second, to analyze the design system performance. And thirdly, to apply the PID controller in improving the steady state system error.
good morning to Dr. Hariza and Dr. Siti. So, my name is Beijun Ho. My metric number is 191061127. So, I'm going to explain the methodology of this mini project. So, firstly, we're going to check the controllability of the system. We're going to use the state space in the PVF form, and we input the matrix A and B into the MATLAB, and we generate the equation and the formulas to calculate the controllability. So the answer is 1 and not equal to 0. So thus we can conclude that this system is a controllable system, and the pole placement controller is able to apply onto these systems. So after that, after we know the system is controllable system, and we giving some situations onto the system. Firstly, the percentage rating is 20%. Setting time is 4 seconds. Third pole is 10 times further than the dominant poles, and the fourth pole is 15 times further than the dominant poles. So this is the situation of the systems. So after that, after we know the situation, we're going to calculate and generate the equation of the pole placement controller. So firstly, we're going to calculate the damping ratio and the natural frequency. After we get these two values, we substitute into the equation, then we get a pole placement controller equation. So this is a compensated system method. So for the uncompensated system, we calculate and we get an equation which full of k unknowns. So we're using these two equations and we compare, and finally we get a k values. So with the add of k values, we can generate the block diagrams of the pole placement controller, which applying onto the systems. So this block diagram will generate the output graph of the system after applying the pole placement controller. So after we use the pole placement controller, we apply again the PID controller onto the systems. So firstly, we use the transfer function just now, and we make it into the closed loop transfer function, and we insert the equation into the Routh-Hurwitz tables. By following the Routh-Hurwitz tables, we can get the value of k and t. So both values will help us to generate the PID controller. So we use these two values and insert into the Zn method table. So by referring to the Zn table, we can get a PID controller equation. So this for the first output. For the second output, same goes with the previous one. They use a SAM method. So after we get a two PID controller equation, we will applying the PID controller onto the pole placement controller systems. So as we can see in the pictures, the first row is a only pole placement controller applying onto the system. For a second row, the PID and the pole placement controller are applying onto the systems. So this block diagram we're going to show the output graph of the system after applying the pole placement controller and the pole placement controller with PID controller. So this is a method that we have used. So thank you so much.
Good day, doctor. I am Lavanya Anak Perempuan Gopal and my metric number is 191061140. Okay, so today I'm going to present the result that we have obtained from our mini project. So this is our original system signal, as you can see. Okay, this is the graph of both angle and displacement outputs for the original system. As you can see here, we have the settling time, which is infinity, peak time infinity, rise time, percentage overshoot, which is 0%, final value is infinity, and the percentage error is also infinity. Okay, so this is our graph for the first output angle after using pole placement controller. Okay, this is the settling time, peak time, rise time, the percentage overshoot is infinity, and the final value is 0, and the percentage error is 0.002. As you can see, there is still a little bit of percentage error after using the pole placement controller. Next, this is the result after using pole placement controller for the output X3, which is displacement. This is the settling time, peak time, rise time, percentage overshoot, final value, and the percentage error, which is quite high, which is 104.89%. This is the combination graph of both outputs with pole placement controller. Next, here we are using pole placement controller and PID controller, and this is the output that we got for the angle for the output X1. This is the settling time, peak time, rise time, percentage overshoot is infinity, and then we have the final value, which is 0, and the percentage error which is 0%. So from here, we can infer that both pole placement and PID controller are beneficial for regulating and enhancing the stable system to control the system. We can either combine the two controllers or just utilize one controller. Our findings show that after applying the pole placement controller, the output graph for the angle exhibits a stable state. However, the signal starts to provide worse output and becomes more unstable after the PID controller is applied to the system once more. We may therefore conclude that since the output angle has a good output after applying pole placement controller, there is no need to apply the PID controller to it. But although the PID controller performs very poorly in overshoot, it does improve the system's settling time and makes it more robust than before in stabilizing the pendulum to reach steady state. Next, this is the displacement graph that we obtain after using pole placement controller together with PID controller. As you can see, this is the settling time, peak time, rise time, percentage overshoot, the final value, and the percentage error is 0%. Whereas when a pole placement controller is applied to the output X3, which is the displacement output, it has the opposite result where it does not function properly. However, when a PID controller is added, the output is enhanced and reaches steady state. Thus, this shows that output X3 displacement needs the help of a PID controller to reduce the system's steady state error. This is the combination graph of both output with pole placement controller and PID controller. And this is a comparison between the output graphs. This is the output for angle and this is the output for displacement. As you can see here, the green line is the graph that we obtain after using PID controller together with a pole placement controller, whereas the blue line represents the system's graph after using a pole placement controller. That's all from me. Thank you.
Hello, my name is Muhammad Shahriza bin Abdul Hay. My metric number 201061320. I will present about the discussion of my mini project of our mini project. In this project, we are required to improve and modify the error of the cut inverted pendulum system. We must reduce and alter the cut inverted pendulum system inaccuracy in this lab. To further improve the system, two additional controller types, which are PID controller and a pole placement controller, must be included. So we must thus review the results from lab 2 that included the pole placement controller. The inverted pendulum system data, transfer function and PVF form state space will all be transferred from lab 2 to this assignment as a reference. First, we resolve the transfer function that was supplied into the state space of the PVF form. After that, we plot the block diagram to generate a graph to observe. The original system, the pole placement controller, was our initial choice for our system improvement. The system's percentage overshoot is set as 20% and the setting time TS is set at 4 seconds. The third and fourth poles are respectively 10 and 15 times further away from the dominant poles. To determine the system controllability before launching the pole placement controller, we must use PVF form state space. There are 4 gains accessible in the system and each gain is determined by comparing the values of the system that have been compensated and those that are not using the MATLAB software. We can create the block diagram once the gains values have been established. The results are plotted once the pole positioning is included. The inverted pendulum system with pole placement controller is then given a PID controller. With the help of a pole placement controller, we first obtain the system transfer function, which is then converted the CLTF for further analysis. we created the necessary equations with the help of the rod width table, and then calculate the gain and time. Then we use the Ziegler-Nichols tuning method to determine each time of the PID controller parameters. To create the complete PID controller equation, the parameter values for calculate PIDs will be added together. We then create the graph after adding the PID controller to the block diagram. We can infer from this assignment that both pole placement and PID controller are beneficial for regulating and enhance the unstable system. To control the system, we can either combine the two controllers or utilize just one controller. Our findings show that after applying the pole placement controller, the output first its angle exhibits a stable state. However, the signal starts to provide worse output and becomes more unstable after the PID controller is applied to the system once more. We may therefore conclude that since the output first its angle has a good output as a result of the application of the pole placement controller, there is no need to apply the PID controller to it. Although the PID controller performs very poorly in overshoot, it improves the system setting line and makes it more robust than before in establishing the pendulum to reach steady state. When the pole placement controller is applied, the output displacement, which has a opposite result from the output angle, does not function properly. However, when a PID controller is added, the output is enhanced and reach the steady state. So, it follows that after using the pole placement controller, output displacement needs the help of a PID controller to reduce the system steady state inaccuracy. Applying the pole placement controller and PID to the inverted pendulum system does not show the perfect results that we want. Hence, we may also use the try and error method to adjust each value of parameters of the PID controller. This method can help us acquire the most accurate results when compared to calculations, but it actually requires more time than the other methods because it must be tried repeatedly until the ideal shape is produced. That's all. Thank you. That's from me. I will pass to Muklis.
Hi, Assalamualaikum. My name is Muhammad Muklis bin Kumardin. Number matric 2010622249. Today I would like to sum up everything that has been stated. The design, the original cut inverted pendulum has a substantially high magnitude of steady state error. And the error was eliminated through the implementation if the proportional integral which is PI controller with Ziegler-Nichols tuning method. Even if the mathematical modeling unknown, it is possible to balance it by evaluating the response of the system and tune each gain until a positive result is achieved. So that's we could understand better on the function of the PI and D in the PID control through application, simulation, and tweaking the gain value to observe the effect of changing the values to the output performance. Through the steady state error was fixed, it's also suggested to apply the usage of more PID control in process to obtain an optimal system performance. That's all for me. Thank you.
That's the end of our mini project. I will show our simulation mini project. That's all from our team, and thank you.